But let's take a step back and look at what is a data pipeline, what is an AI pipeline, and what's going on under the covers on the software side. So you're starting out with data ingestion, feeding it through a process of firstly cleaning the data, labeling the data, where you're applying supervised learning, perhaps applying some feature engineering. And then when you get into training, the data scientists are looking at what frameworks am I going to operate on, what parameters am I going to tune, performing the model training itself, evaluating the results of that model training, and then start to build out deployment and inference. So the pipeline, when you start to double click on it, is a variety of these stages. Now what is interesting is each of these stages is a performance bottleneck. You've got data bottlenecks with ingestion. You've got aggregation bottlenecks across multiple sites. CPUs become a bottleneck when you're looking at data prep on CPU clusters. And then the obvious conversation around training bottlenecks. And what system architects are doing right now is looking at how you solve each bottleneck across these stages. Can you start to offload from CPUs to GPUs? Can you use RDMA to offload the network ingestion? Can you shift left with some of this intelligent processing to avoid the bottleneck in the core? And what do you do to move the entire process to the edge so that you're never coming into the core to run this life cycle? From the life cycle of a training job, there's two things that we're looking at. We're looking at data, and we're looking at frameworks. And when we get into data, we start looking at what is the type of data. Is it structured? Is it unstructured? If it is structured, what is the data source? Is it a database? Is it a GPU database? Can it be co-located on the GPU compute? If it is unstructured, is it file? Is it object? Is it parallel file systems? And so those are the choices. You start getting down to, OK, what is my data type? What is the data source? How many data sources? Where are they located? Close to GPU or a cached instance by the GPU? And then the frameworks, of course, which is every developer or data scientist has their own choice of framework. When you get into the actual data that is being trained, these files that are being trained, depending on whether it's image, video, or audio, you have random reads of images, which is the most basic type of training file read. Or you've got aggregated images in the form of TF record, that's a sequential read, or a sequential read of audio or video streams. One training job may run as much as a month. A really complex training job may run an entire month. More typically, it's probably a day or a couple of days. That epoch or that training life cycle is one run through the training infrastructure, and then off you go again. So let's look at what does that all imply. So we're taking data in the form of images, random images, feeding it through these neural networks on GPU compute hardware. Layers of these neural networks are operating on different sets of hyperparameters, producing an output from that neural network that eventually turns into a trained neural network for that use case, using different types of neural networks for different use cases. The thing they have in common is random reads of images or video or audio files, significant amount of compute processing, while parallel reads continue to occur into the CPU pipeline. So this is a phased job where CPU is reading data from I/O into CPU pipelines, staging the data while the GPU is operating on the training jobs, and then more data is fed in from CPU into GPU. The more the number of layers, the more compute intensive the job. The more shallow the network, the more data intensive the job. And on that note, you get into the conversation around training and inferencing. So training and inferencing are important because these are entirely different infrastructures. Everything I showed you so far, those 12 kilowatt racks, liquid cooled cabinets, all of that tends to be the training jobs, where you're running workloads for a month on end just on a single training job. Once you have trained the neural network, that trained neural network moves into the inference validation systems, which tend to be more CPU heavy, but with a little bit of GPU to run through the inference validation. Completely different clusters, entirely different. One may be a DGX cluster, the other may be a FlexPod or a white box CPU cluster with some GPUs. What does this look like from the data scientist? He's selected a framework, he's off, he's ready to go, he's got his Jupyter notebooks and IDE. He's picked a model that he's going to tune and a set of hyperparameters. He's read data from storage close to the pod. So this is where the pod comes in and data has been cached close to the GPU. And now he's building these TensorFlow threads that start to build up data flows into the GPUs and starts to then run the model through the epoch, sync the results from the model, and off you go again and again. What does that look from a storage perspective? Why does storage matter? What is storage doing in here? The number one goal is to keep the data scientist busy, which means you're going to be loading up those GPU systems to 100% utilization, which means you've got data flowing into the GPU constantly. That data is being read in the form of random reads of small images. Each image that is read may be a single record of itself, or you can aggregate a set of images into a single TF record aggregated file. Each file is read by a single reader job that is now mapped from a locality perspective to the set of GPUs or the cores, the tensor cores of these GPUs, and then you're now running through these training jumps. You complete one pass of the neural network, and then you read the data again with a lot of random switching, not only across GPUs, but across nodes themselves. So what's going on here? You've got a parallel file system, or at least some kind of scale-out file system. You've got a scale-out compute cluster with random reads across this cluster, doing mostly read jobs. So 80, if not 100% of the data is being read, with checkpoints that cause sequential writes, or synthetic data generation called GAN neural networks that again cause sequential writes. A combination of random reads, sequential writes. And where have we seen that before? We've probably rarely seen that before. Random reads in an OLTP database, that's something we see. Sequential reads in an analytics engine like Spark or an Oracle Exadata. But the combination of the two, not as often. So what did we cover so far? We covered the pipeline, the process of ingestion, the double click on the training cluster, and what are the bottlenecks, the system architecture bottlenecks that require a high performance compute along with high performance data, and the ability to bring random reads alongside with sequential reads and sequential writes. Very, very unique workload.